We consider now another example whereas an exact solution can be seen, and that is for a flow in the entrance region of a circular pipe. So after we consider the flow in the entrance region of a circular pipe, then we allow the fluid to be flowing, and then after transition position have taken place and they have died out, that is after the initial disturbances that occur when the fluid flow is generated, then a laminar steady flow takes place, and in that situation the fluid flow is fully developed, and therefore it is represented by equation 19 that we have given earlier, and it is approximated the value of velocity component, and the mean value of the velocity component is given by Wm equal to dw by dz, and that's obtained to be of this value, where the Wm is equal to 2 over a square integral from 0 to a r into w dr. Wm is the average velocity or the mean velocity over the cross section. The first equation, it has the solution WRZ to be equal to this function. Now, the important thing to note here is that since the geometry is cylindrical, whenever the geometry is cylindrical, the solutions, the function, the solution of the Laplacian equation mainly represents, or they involve, what we call as Bessel functions. And the Bessel functions are denoted by J1 or J2, or let me write it in the form of by Jn depending upon, of course, R. Now this is Jn can be written in the form of series solution, and it's known as the special functions that occur in the problems of physics and chemistry. The Jn normally occurs when we are solving a problem related to circular matter, and when we are solving the Laplacian equation, let's say delta 2 psi is equal to 0 in cylindrical polar coordinates, then the solution psi will involve, it will have JNR, the Bessel function, in its solution. So we are using that result that we do in partial differential equation or solutions of partial differential equation or Laplacian in rectangular coordinates, cylindrical coordinates, and spherical coordinates. And you will recall, of course, in rectangular coordinates it's simple x and y, but in cylindrical coordinates the solutions are reflected in terms of Bessel's function, and in spherical coordinates they are reflected in terms of Legendre functions. So here we are concerned with the Bessel function, and the notation here is reflected to J naught, where this is a standard result and can be found in any book of partial differential equation. The value of pressure or pressure behavior is reflected, is given by this equation. And of course I have explained the existence of Bessel's functions. And here, a little more about the same J1 and J2. So the variable eta are the roots of the equation of Bessel functions J2, eta and equal to 0. And as I said, Bessel functions is a set of series solution, set of summation of series, infinite series, and this solution represent this, and the solution can be determined by calculating the roots of this equation. This is an infinite series, and it's not possible to find out analytically. So therefore, normally the Bessel functions are obtained numerically. By giving different values, we evaluate them, we find them out for different values of the variable under consideration. And of course giving numbers. So if we keep changing this n, and it runs from 0 to infinity or 1 to infinity, so for n1 it will be different, for eta 2 it will be different, and we can continue like this forever. Here some sample solutions up to eta 6 are they have been calculated and they are shown here.